So yeah, I'm Jake Gillberg, and this is Christian Crawford, and our talk is called RChain from Process Calculi to Tools for a New Economic Age. I suppose I should start by saying that I found RChain about 2 years ago when I quit my job and I was like, what is this Ethereum thing all about? And was trying to learn more about Casper. Was on one of the Casper Hangouts and heard Greg Meredith, who's the president of RChain, talking about some math that was like completely and totally opaque to me. I had no idea what was going on. But it sounded like there was some weight given to the ideas that he said, and it sounded like he had like a good sort of notion or mathematical framework to think about concurrency, distributed computation, and how it all applied to the blockchain. So I was really interested, and I wanted to dig further into some of the literature behind that to see if it was just sort of all kind of fake, or if there was some interesting and deep things going on there. And I've 2 years later, I still think there's some really interesting and deep and cool things going on there. Before we get into this a little bit, do you want to introduce yourself, Christian?
I guess. My name is Christian. I'm from like logic, proof theory, and philosophy, and stuff like that. I'm a developer as well. And I am implementing RChain. That's about it.
Okay, cool. Yeah, awesome. So what RChain is in terms of an organization, there are two cooperatives. There's a Washington State Consumer Cooperative based in Seattle. That's where sort of the hub of RChain has been before. And there's also just been founded a German cooperative, sort of headquartered in Berlin, with kind of a completely different board. I think the president is on both seats, but the Washington State Consumer Cooperative contracts a company called Pyrofex to do development work, and these slides will be available afterwards. I tried to pepper this thing with links if you wanted to go into there after. And they host a research program, and with researchers like Luke Ong from Oxford and John Baez from UC Riverside, and a few of his students are working on some RChain related research topics. Inside of the Washington Cooperative, there's also a company called RChain Solutions, which offers like RChain specific consulting. It also runs a community bounty program. The German cooperative is tasked with building governance tools. And then there's also two venture capitalist firms, arms of the RChain Cooperative, two funds, and those are Reflective Ventures and Pythia. So if you have an idea of an application that you'd like to build on top of RChain and are looking for funding, these would be great people to talk to.
And they got money raised from the RChain funding, public funding, and so they're acting on a mandate for RChain.
Yeah. Yes. Mm-hmm. So from a high level, here's sort of the technology that makes up RChain. It's Vlad's CVC Casper consensus. So they're sort of really in deep communication with Vlad and the work that he's doing on his consensus protocols, and are pretty committed to sort of implementing those ideas in the fullest. It is, in terms of like sharding type stuff, it's multiple block DAGs, and with the Rev, which is like the ETH, it's the staking coin. In all of the child DAGs are locked up in a contract on the parent DAG. So you can sort of get this, you can have these child shards which have high performance, high bandwidth, high storage capacity, but might not have as much security in terms of consensus or amount of stake that's generated. So the hope is to form some sort of like continuum of performance and security. But really, those two things, they're like kind of cool, but I don't think they're like super unique to RChain. There's a bunch of other projects who are sort of thinking about proof of stake and block DAGs and these sort of like sidechain looking like structures. The real innovation here, I think, is Rholang, which is the virtual language, or it's really a high-level language, though, that the smart contracts are written in. And so that's what I want to dive into with you all today, or what we both want to dive into.
Oh man. Okay, so What helps sort of frame the conversation is looking at like how these different things have evolved, how blockchains evolved, and the way essentially what we gain consensus around has evolved. Bitcoin is mostly just database transactions. You know, it's like the wallets that are at play and how our coins distribute between the wallets, and those are like the primary operations of what consensus is gained. Ethereum makes a big innovation there, insofar as that what you gain consensus around are the execution programs themselves. So you have Solidity, which compiles down to EVM, which is a imperative assembly language. And so then we begin to be able to think about smart contracts in a larger sense, and start to be able to construe the programs that are running on the blockchain as smart contracts. What RChain does is it introduces concurrency, which is very difficult to handle in Ethereum. And the rewrites, if you know anything about like rewrite theory and logic and whatnot, it's like how function application works in logic calculus. You do substitution and so forth. Except here it's using channels to be able to have communication between processes. And these steps of communication is essentially what you gain consensus around on the blockchain. And so, to be a little bit geeky here, with the Curry-Hart isomorphism, the isomorphism for between proofs and programs, proofs as programs, as smart contracts, and I'll say a little bit more about this later, as games. And then this is the row calculus. So I'll get over here to the point. This is like standard BNF notation. And so this is the output clause.
So it's just so you understand, if you're reading that in plain English, you're saying P or Q are of the form.
Yeah. So P and Q is of the form. So these are all the things that a process can be. It's a recursive definition. So in here can fit any one of these different things. So this is sending a process across the channel X. You see down here, X and Y is what is called a quoted process. So the names or the channels are simply the quote of a process which designates the name. And names and channels are entirely equivalent. So you're able to send a process across a name which is a quoted process. And then this is the output or input guarding clause. And here we have name X, name Y, name X, name Y, and so there are a series of them joined together. So what this is saying is, there should be a P here, that's the body, is the continuation. But what we're saying is there's listing on Y1, we're listing on Yn, and we receive the processes that we send as names. And so when they get sent across, they get quoted. And so, in the continuation, that's wherever X1 appears in the continuation, it gets replaced by the name that we received on Y1. And same with all of these. So the name we receive across Yn, we receive across Xn. And then P...
Sorry, I'm just going to actually put that in there right now.
Okay, yeah, go ahead. Do you like the curly braces too?
Yeah.
It's more like Rholang,
Yeah,
right, calculus.
Yeah.
And then this is parallel composition. This is two processes composed in parallel. This will make more sense when I go over the comms rule. It's essentially, anything that's P, anything that's Q, which is anything that's right here, can be composed together in parallel. And then this is more of like a row calculus presented kind of more of a Rholang way. This isn't native to just row calculus. It's more like namespace logic. But this is creating a new private name. And so the only way this private name can escape through here is we get sent across a name that goes outside of this. And so this, so we're saying there's a new X within a process, and somewhere in this process we use X as a name. And then this is the dequoting. So if we receive a process as a name, and we want to execute it as a process, we can decode it. Or, so if we want to execute it, or if we receive a process as a name, we want to send it across another process, we decode it. And so that's kind of how that works. So it's not, with Rholang, it's not just coded processes, but it's also the new names that are spun up from the new operator here. And so here is the comms rule, and this is where all the dynamism and interaction comes from Rholang. So here we have input guarded clause composed in parallel with output guarded clauses. And so here we're sending out processes across these names. So we send Q, and then this is more like sort of like this syntactic form. Like this wouldn't actually execute because what is Y1 and so forth, we'd have to use like new, or it would have to actually be a channel to like add some process. We're sending Q1 across Y1. So what would happen is that we receive at Q1. So X1 would be bound as at Q1. And anywhere in P where X1 appears, that will be substituted for at Q1, whatever Q1 is. And it could be any process as we find over there. Likewise for this. And so the comms rule here, this is kind of like proof theory notation of like substitution. So we're saying P, which is a continuation, and we're saying that everywhere in Q, or everywhere in P, at Q1 replaces X1, and so forth, until at Q in replaces X in P. And then you just apply that rule recursively. And it's kind of the only reduction rule in the row calculus. We also have the fact that if we quote a process, then we dequote it, it reduces to the process. So if like in here, in P, we had like star X1, then we get star at Q1, and that would just resolve to Q1. And then with Rholang, we also have reduction rules for, say, binary operators in standard arithmetic and so forth. But for the most part, this is how the execution model functions. Yes.
Can I ask some questions?
Absolutely.
So, like for the beginning, P and Q are meant to be P is a process and Q is a coded process?
No, they're both processes.
It's just processes.
Yeah, the reason why you have PQ is it's like sort of like BNF representation of syntax. So saying P or Q could be anything that's defined on the right.
Oh, it's just a P or Q. That's it. Okay.
Right. It's a recursive definition.
Yeah.
So this, so you could this.
So P and Q can be both this. Oh, and we need P and Q because we have like the parallel things.
Yeah.
So we need to have two variables.
Right. And so here this is P because P is defined as any of these. This could actually be P par Q. This is par.
Okay.
So
X and Y are quoted P's. This is pretty recursive. So where does it even start? It needs to have like
yeah. So there's also this. We don't have it up there, but there's the zero process, the stop process, which is so process is the ground level entity, and you just say this is a ground level process 0, and everything is constructed.
Okay, because like the recursion needs to end somewhere.
Yes.
Yeah.
That's where it ends.
Okay.
Yeah, and the zero process, or with Rholang, ends in like one of like the base, integer, string, boolean, whatever.
They're all ground level.
Yeah.
Stop processes that have no commutation associated with them. No computational steps associated with them.
Yeah. So things that.
So a process and a name are kind of the same thing because a name is a total process.
Yeah, exactly. And so you can like whenever you want, you can change a name into a process. You can change a process into a name.
Do we have examples?
Yeah, we will. Yes. We'll have plenty of examples.
I think just if all that, I know that was like took me a while and a few catches to understand this stuff, but I think really like the basics that you want to get out of this slide is that you have sort of these two types of processes. You have processes that are like sitting there and waiting and listening for information. You can think of them maybe as like functions that are like waiting for arguments, messages to come in, and then they're going to like do something with those arguments, and they're going to become another process.
So like kind of like actors receiving messages.
Yeah, you can yeah.
Yeah.
This isn't the actor model, but you can sort of like push actor model. You can push those two kind of theories of concurrency together.
And then what he's talking about here is that here you have something listening, and when you satisfy all of these things that it's listening on, which gets sent from here, you execute that. So this is waiting, this is sending, and when these send, it satisfies these conditions and executes that process.
So we have a whole bunch of different computational entities passing messages back and forth between each other, and that's like our whole theory of computation. Is that?
Okay, so as soon as like all x1 to y1 to yn are basically and I finish calculating, I can then start calculating p.
So right. Well, it's not like the calculation would happen probably like over here.
Yeah.
It's like when all of the sends occur, then you fire the p. But you could also actually have things sending, and then they're waiting to be listened on. And it's not until you apply the comms rule enough to get the thing that actually begins to listen on them, and then it has everything that it needs, and then it fires p. And applies the comms rule again on p. It's like p could be then like something else like this, or something like this, in parallel with them.
Let's keep going.
Okay.
We got quite a few slides.
So this is like the sort of like execution model, which sort of ties into like how this is similar but also different to Ethereum. This is from like an old architecture document, so like this notation is kind of wrong, but here we have things that are sending and they come over here. So this is a process that sends, this is a process that receives, then executes the continuation with the appropriate substitutions in its continuation. And then here you can see how it ends up becoming a blockchain, is because the steps, each application of the comms rule becomes a state transition. These state transitions are recorded on the blockchain. So each comms rule is a transaction. These transactions are all serialized into a block, and then that block, that consensus is gained around.
And so no, right here, like the transaction on the left-hand side and the transaction on the right-hand side, you haven't actually ordered those.
Yeah.
Because there's no reason to order them. If you have a mailbox here, message putting it over here, and you have an entity over here, messaging passing over here, like. The blocks are still going to end up being ordered, but those transactions within the block are not ordered.
Of course, like this one is ordered as interior to that one. So like the continuation that fires here, like the fact that this fires first is an ordering in terms of like information flowing from output guarded clauses into input guarded clauses and firing continuations, and that process recursively occurring. Okay, so here's an example. This is the Hello Road example, and it uses a lot of key things here. We're using the new, and we're defining a new name called standard output. And you don't always need this, but because we want to output to the node standard output, there's a way to specify special types of channels with this. And this is like row input output standard out. And so what we then do is, now that we have this within this scope, we're defining a for clause. And this for clause is listening on a name, and a name is a serialized process. And so we have the string mailbox. The string mailbox is a process, and when we quote it, it becomes a name. So we're listening on this, and wherever x appears in the continuation, which is this right here, what we receive in this as a name will be substituted in here. So here we're sending on the name, which is the quoted process mailbox, the string, and you send processes hello world. And so what happens, how it would execute is that X, we send processes, and we receive names. So we would receive at string hello world, and then X in here gets substituted for at hello world. So star at string hello world reduces to hello world, and so then we would send the string process hello world through std out. So we receive names. What we receive on standard output is at string hello world.
And then I also just want to point out too that the bar in between the for clause, which is listening, and the mailbox right here, this is parallel, right? So these two could be separated from each other. You know, they're running at the same time, right? The fact that this is written before this one doesn't really mean anything.
No. So it's just like all the things that are running in parallel. It looks, see how it can match, and then reduce sends and inputs to the continuation, and just applies that composable again. Yeah. And so this is the idea of unforgeable names is that they're made from the new operator, and access to them is limited only to those processes which have been legitimately passed. Because it is a blockchain, new names end up becoming hashes. Anybody could look at the public blockchain, get the hash and whatnot. But if you try to hack that in, it wouldn't, and no consensus would be gained around it because you have not legitimately acquired the hash for that name. So it's like a capability system, which we will say a little bit more about. And yes, so that's like the summary of that slide.
The other example is like in Java, your object pointers are an integer, but you can't like take an integer in Java and turn it into like an object pointer reference and then all of a sudden access that object. This is a similar thing here.
Yeah. And then bundles, they're a bit of a newer feature, although they've been thought about for quite some time. And it's a way to enclose a process to make it impossible to pattern match or extract names from within it, which say a little bit more about process matching, as well as restricting read and write access when those processes are used as names. It sort of like replaces the idea of I/O pairs. If you guys know anything about Rholang, like, I don't know, 2 or 3 months ago. But the syntax is like this. And so bundle P takes process P and wraps it up. So now you cannot extract any of the processes there. You can see if this bundle is equal to another bundle, but that's all that you can do. But you can send and you can receive messages on this if you quote it and use it as a name. With this one, you can only send on this. So this is a write-only channel, whereas this is a read-only channel. So if you want it to like distribute to the world a write-only channel, but you don't want anybody to be able to intercept these messages, then you send out a bundle that is write-only, and then anybody can write across it, but only you can access that information. And you can also do it the other way around. This you cannot read and you cannot write on. And here's some examples of like the equivalents. Essentially, what all those examples are is that when you compose bundles, I can compose I can compose bundle P with bundle minus Q, and it becomes bundle minus P par Q. And so the bundles get flattened, but then the resulting bundle ends up being like sort of like the set theoretic union of the restriction. So here, if we try to compose a write-only name and a read-only name, you end up with a name that you can't read or write on. they're essentially used for constraining read-or-write access. And there's also another useful feature called the challenge, which we will get to shortly. Okay, yeah, let's do that. Let's get this one too.
Yeah.
I mean,
Let's just start here. We can go to matching stuff later. I don't think we really need that right now.
yeah, I mean, it is very
Yeah,
important because
right.
that's where like the reflective aspect comes in, and it's essentially like when you receive names, you can like match the structure of a name. So if any of you guys like know like OCaml or Scala or something like that, like if you get like a complex structured process, you can actually, rather than interpreting it all as one single variable, you can actually chop it up and pattern match different parts of the structure of that quoted process that you're receiving. And then
Yeah. Cool. And those patterns become just like almost like symbol types. Almost.
yeah, they're called spatial types.
All right. So that's Rholang, kind of in a nutshell, and the parts that we need for the rest of this presentation. But I think we're gonna sort of move on a little bit to sort of the next layer, and this is moving beyond access control lists for sort of defining the behavior of your programs and the sort of security properties of your programs. So the problem with access control lists, which is sort of like Unix file permissions or something like that, is that you have this confused deputy problem and ambient authority problem. So access control list systems construe authority based on identity instead of purpose. So when I'm running a program, it says, and I'm running the program as my user Jake, then that program gets all the permissions that Jake has. So an example is if the program has access to the network for updates, it's like Microsoft Word or something, and it also has access to opening up files for reading, it now has the authority to sort of compose those two things together and send my file across the network, right? Even though that might not be, I only wanted it to sort of like read my file in a specific way. So in Solidity, you sort of really have this access control list way of talking about permissions. When you think about it, anyone has the right to call a function. It's the function's job to sort of like kick out with modifiers anyone who doesn't have access to the function. And the way you usually do that is look at like message.sender, but when you add in like proxy contracts and all that to sort of like try to get at some sort of identity, but really you want these like sort of like modular expressive sort of permissions control, which is just like really hard to do when you're trying to do anything complicated in Solidity. So there is this concept of object capabilities, which is more of a rights-based approach to security, and so it kind of, you can think of it as bringing the social and legal concept of rights into computation, allows that granular specification of rights, and really allows you to talk about the distribution of those rights. This is done by removing the distinction, separation between designation and authority. So if I can do something, I can also like delegate or designate that authority that I have to someone else, and they are able to do the similar thing. So it's kind of like the rights to interact with an object are like really strongly attached to the object itself, and that object is getting passed to other people. Yeah?
Why is this a concern of the platform and not on the application layer, how rights are handled?
So it is a concern on the application layer, not necessarily on the platform layer, right?
But it's just a library, the OCAP. You
The
can also
OCAP's
use it the traditional way.
Oh, so we'll talk about how you actually like implement OCAP like capabilities within Rholang in a minute here. It's really the concepts of that we've introduced in Rholang about these like bundles and other things are like very tightly really at their core about these sorts of object capabilities.
This is kind of example.
Yeah, we'll have some examples.
This is an example.
So yeah, some examples you can think about, and these are kind of like hand wavy right now, like you can think about.
Or or just rephrase why is OCAP so important?
There's a few more slides. The main thing, there's a slide that's coming up called the inextricability of designation and authority. But the main thing is how do you forge things. If you are a program and you have access to everything that a certain user has, you can read their files, write their files. They aren't given just the sole minimal authority that they need. You know, which is like another big, larger principle in OCAP is the principle of least authority. The idea that excess authority leads to abuse of authority. And so then, rather than access control list style where it's identity based, it's more like functional purpose. Like, what is the minimal set of functionality?
Why do you say in Ethereum it's different?
Because Ethereum is not an OCAP system.
It's an ACL system.
OCAP, as we agreed, belongs to the application layer, not to the protocol layer.
Okay, so it's very, very difficult to build OCAP looking applications on top of Ethereum.
Yeah. In its current form, you might.
Sure. Yeah. Cool.
The system, even though that they're implementing the application layer, different systems are sort of like differently afforded by, differentially afford object capabilities. Like for example, we might say a file system is a system layer, and the programs that are running are application layer, but the file system is certainly an ACL system.
And Ethereum has no notion of any rights management, so therefore it's all in the application. We cannot say that Ethereum is genuinely not OCAP but an ACL system. We cannot say that.
Sure, maybe Solidity.
And it would be
is
wrong.
the better one to talk about.
If RChain would say we are an OCAP system, I would say that's a pity. It's not what you have to do.
No, yeah, it's more than that. I think it's definitely more than that. I think we're moving on. Like the OCAP capabilities are really like one of the core reasons I sort of want to build on top of RChain right now instead of Ethereum for some of these applications, and we'll get to like why and what types of applications we see and why OCAP is sort of like a necessary component of that.
But the unforgeability, like, is where, like, even though Rholang's not OCAP, like, the fact that names are unforgeable, that we have unforgeable names, makes it very OCAP-y. So if you consider the fact that, you know, I only can read and write on names that I have access to, and I can sort of have discretion over how I distribute these names. That and there also might be other names that can be.
What is the difference having a private variable in a Ethereum smart contract and having an unforgeable name? What are the advantages?
Who can write on the variable? You know, if you have this like public contract, you know, what if you want to differentially? Like what you could do in Solidity is say like in advance like when you interact with this contract.
Nobody can write to this variable.
Right. But like the thing is like when you get to just the granularity of names, it's not like you're specifying like in order to interact with this contract, I'm setting conditions. It's more like I make a contract, I keep it hidden, and then I selectively distribute it, so it's not about like specifying a module that like checks authority, but rather distributes authority without necessarily having to check it because you are sending the authority with discretion, and it's a functional piece of authority.
Yeah. So here's some examples of some OCAPs and pictures. if we have a file system, then we can think of like getting and setting the bytes as sort of two different functions of it. We can create maybe something called a read facet that only has access to the get bytes, and then we could sort of send this read facet to someone else, some program, and then we don't even have to worry about, you know, like protecting our set bytes function down here and like kicking out someone who wants to access this. Because we know that, you know, really the only object that this other program has is this read facet, so they can only read my file. Here's like a revocable forwarder. So say I like pass all the permissions to my file to this entity up here, which really sort of brings out two capabilities. We have both a forwarder and a revoker, and we can pass these to two different entities. So maybe we don't trust someone to like do with any of our file permissions. We don't trust them to read or write to our file, but we do trust them to, if they see someone accessing the file incorrectly, be able to call this revoke function, which can destroy this link to the forwarder, meaning that like anyone who had held this object and was using it to access the permissions of the file no longer has access to the file. And then we can think about like composing these things together, right? So we can think about like a file, and then a read facet, and then like a revocable forwarder on just that read facet. So we have this like composable idea of security. The permissions and access and authority and rights for an object sort of start with the right, with the object itself, and then the object itself is sort of responsible for passing them out. So here is an example of like an OCAP way in Rholang to talk about something like a code check. So we think about a code check as maybe like a creator of a code check. They set up something inside of a theater, and so they sort of have the sole access to say like, yes, you can have access to this code check desk to check your code or not, and they say maybe open access, you know, between 9 a.m. and 5 p.m. or something. And then when you think about a person who's checking a code, they're given the right through the form of a ticket to get back the thing that they checked. And then they also want to know that no one else has the right to remove their code. So here is an example in Rholang. So we define this new private variable code check. Really is what we're going to be listening on. We are listening on make code check. So this is the code check creator is going to end up calling this. It's going to return something.
We should mention like contract to syntactic sugar.
Oh yeah.
So remember we had the fors and input guard clauses. A contract syntactic sugar for a persistent one. So normal input guarding clauses, they listen to see if all the warning conditions are satisfied. Once they execute the continuation, and they disappear. The contract, there's also a for instead of doing the single arrow, you do a double arrow, and it's entirely equivalent to the contract.
Well, maybe not when we have pins.
Okay, sure.
Yeah.
But the point here, though, is that with a normal for, we would be listening on make code check for the variable return. And then once we call make code check with a return channel that we send across it, we would not go send across make code check. But we want this to be a persistent input guarded clause, persistent contract, and so then we can send it at however many returns, and it executes the continuation each time with each different process that we send across it.
So you can think of this as kind of like its own contract factory, object factory, pretty much. So we provide some new private names, which are going to kind of be like our object capabilities, which is the desk and the closet. The desk being the thing that people who are approaching the code check interact with, and the closet where we're going to be storing their codes. And then we return to the person who instantiated this make code check. They specify the channel on which they want to receive back, the object that they just created. And so we're going to return to them this desc object that can only be sent on. So we now know that the owner has the name for a desk, and they can pass that out to anyone, and they can also be assured that only their code check that they created has access to read messages coming in on that name, so you don't have to worry about interception, someone intercepting someone at the desk.
And then you can give the desk name to anybody that you want to be able to give their code and pass behind the desk, put it in the closet.
Yeah, and you could put that behind any amount of these like revocable forwarders or any other of these sorts of things. And so now we're gonna, at the desk, what we're gonna be doing is we're gonna be listening for someone saying, I want to check in my code. So we're gonna interact with it by sending like the string new, and then they're gonna send their code along.
And this is a persistent form, as you see, so you could also write contract, bundle desk, and then have new code return as arguments.
Yep. So for each code, we're going to generate a new ticket, and we are going to return to that person their ticket, and then we're going to use, so we're going to forge a name here, a private name. So we're going to use both the ticket and the closet private names to generate a new name here, and that name is where we're going to store the code. So this is like creating a little like cubby in the back closet, and actually, rather than a ticket, it's more like a key. We're locking up in a cubby in the closet someone's code, and then we're giving them the key, and then we're not retaining a reference to ticket here, so actually like we can't even, the contract itself that stored this code can't even access and grab that code back out of. It will need to be returned the key or the ticket for the code to be able to return.
And this is where the inextricability of designation authority come in, because there are two secrets here. One is the secret that is closet, which is kept completely internal to make code check. It is not distributed. The other one is the ticket. The contract does not retain the ticket. So if it wants to be able to read across all of the things that has been stored, it needs to get it from somewhere. Namely, it needs to get it from the get. So only if somebody sends the ticket back across the get are they able to reforge that name. Because the base names are unforgeable, and only if you have both names can you forge the name across which the value has been stored, and then be able to get that value back.
Great. Yeah. All right.
Okay. So let's say like a few things. This is more of like what we're working on right now in code, and designing, and inspecting out, and like where I think like things head to in the future for RChain. And it comes down to something like the OCAP, the redesignability of economy. And object capabilities, when taken to its conclusion, it's about articulating the structure and distribution of rights within an interactive system. And this makes it an incredibly useful paradigm for programming and governance in like modular expressive ways where you exercise very granular control of the distribution of these rights, of these capabilities. And Rholang is both a capability system and excellent for concurrency, making it very, very ideal for economic structuration. The history of political economy is really the history of political and economic governance forms. So we're reaching a point where we can formalize the very structure of economy and governance in a way that we can formally prove properties about. But not only that, we can also create group properties about new governance structures, new economic structures that we haven't seen. We can do old things, corporations, cooperatives, but like what lies around the corner? I think that there's a lot of room for redesign and re-experimentation to see what else that we can do. And so I say just a few crazy things about like the crafting of languages for the logical reconstruction of economy. Logic, if you look at the latest literature, is a game. It's process calculi like row calculus and linear logic, and game semantics, all these different things, predicate the execution model, which in logic is called proof normalization, in terms of interaction. Interaction becomes computation. You're able to put these complex interactions on a blockchain. Suddenly you have a computational system that you can interact with and be able to interact with complex economic structures that are running some distributed consensus as a blockchain. Another important part is the resource sensitivity of what we use, which Rholang is resource sensitive. You can only receive a process once. The fors that are not persistent can only listen once, and so forth, which is sort of related to double spending problems and so forth. And that they're related, they're linear resources, somewhat the counterpart of object, the logical counterpart of object capabilities. Being able to formulate logic into an interactive game, I already said that. And so, another part is that recent findings suggest logic doesn't really have an ultimate foundation, and that truth is contingent on the interaction of various resources. And so there's a game of testing various logical resources against each other to see which logical resource wins. The interaction of this is computation. And then the other half of this is economy as a game. Economy is all about logical structure, not just of governance, but also behaviors of agents within systems afforded by their capabilities. And so economic interaction is interaction with economic strategies within a game. And anti-foundationalism economy means there's no ultimate form of economy, but it means that the interaction of logical strategies is subject to contestation and subject to being able to create different forms of interaction, see how they play out, like let it experiment and see what wins. And can we make new forms that compete at a large scale? And so the need for artificial languages like Rholang are necessary to be able to formulate these new economic structures and these new economic strategies. It begins with something like process capital, where we can get like the governance infrastructure of blockchain, but we also need, compositional approach to mechanism design, game theory, to create languages that produce like tractable challenges to this economic status quo, and being able to design for various behaviors and incentives. And sociality emerges from game structure. Games involve the interaction of moves within articulated rules. This applies to economy equally along with the way that we socially relate with the logic of economy in terms of how we are able to interact with it. And so the expansion of the capacity of our languages for articulating economic structure expands the moves that we have within a game. If we have a better language, allows us to express more sophisticated structure and new structure, then we expand our degrees of freedom in terms of economic experimentation. The interaction with the systems we build is crucial. Everything from user experience to the sustainability of the economic models that are around the governing structures, the viability and accessibility of our systems. Is it can anybody take Lego blocks and put together a new economic structure, or do they have to be programmers? Questions like that are all necessary questions for the success of it. The design of economic structure, it needs to be connected with design in terms of its ability to craft and emergent sociality in terms of the types of behaviors it incentivizes and affords. So our craft can, we can set, we want these types of behaviors, and we can craft towards these behaviors. It's what things like mechanism design, compositional game theory are tackling. The last thing that I say is just a few words like what I'm doing. We're building something called space. It's essentially grammar for the expression of economic forms in a very modular and expressive way. It needs an object capability approach. We tried to use Ethereum, it didn't work. We tried to use ERC20 tokens, like a capability token, and then being able to check if you want to interact with this contract, you need to have this capability token and whatnot. It just was way too intractable. has three main concepts. It's the offer, takes slots, be they values, tokens, processes, or whatever, then executes the process of the offer. You know, it's very much like a complex input guarding clause in Rholang, where you know, a persistent offer is like a persistent contract, or just a single for is a one-time offer and it listens for certain criteria which satisfy it. And then token is more expanded sense than what we are usually thinking of tokens. It could be a capability token. So there's an offer that executes and gives me access to a certain resource. I can have this token, I can invoke the offer, and then I can gain access to that type of resource. You know, maybe it's like an offer to make a proposal. If I have the right to make a proposal token, and I can invoke that with the offer, you know, add some other inputs, other slots, and be like, oh, you know, I want this to be a proposal within this type of organization. And it can also be a currency, you know, that is one of the slots for the offer. You can check for certain types of currency, or it can be a name to a resource, or even a reference to an offer. So you, if you want to keep an offer private, you don't even need a capability token for that. You just turn the name of the offer into a token, you pass it along, and they can spin it back into an offer. And then constellation is economic relationality broadly construed. It could be an exchange, business, cooperative, or something else altogether. And a constellation just emerges as a surface of offers which are associated by the way that they can all be forged from the name of the constellation. And so they are the names for the offers are forged from the name of the constellation. And they also share internal methods and offers from which they are composed. Because offers can be chained together, the outputs of certain offers can go into other offers and so forth. But then there's also, you know, it might have like certain key functionality within like a governance structure that you then want to embed in the back doors of all these different offers. But that's a very key functionality. So you only share that sub-offer with these other offers, and part of what makes this surface of offers a part of the same governance structure, they share access to this key component. And a large emphasis is on compositionality, possibility. We've been able to model a large amount of existing organizational forms, the old ones. You know, we're specking things out, drafting them every day. It's very easy to couch a governance design within the terms of space. The three components are very composable, expressive, and intricately related in nature. Now, Jake's going to talk about a few things that he is interested in.
Yeah, great. So what I'm interested in is sort of like, as a software developer, I kind of want to build the commons. I want to build things that are good for other people, good for humanity, good for the world. And so when this is just like a software developer's perspective, but when I look at like, you know, where am I going to work? How am I going to spend my time? You know, I can either think about like working for an open source project or working for some sort of private company. When I'm thinking about an open source project, you know, I can maybe get compensated for it if the work that I'm doing is very generic and it's like framework type work that a bunch of other private companies are using. Or I can make something that's like useful to end users and like sort of more of the thing that I would think of as useful, but then I kind of maybe am relying on charity to drive my work. And then I can think about maybe working for a private company where you know, I sort of get compensated, but I have this outstanding order to purchase my labor, and that we have corporate success is sort of maintaining control of the product and the revenue stream of that product, and the company, you know, retains the rights to my work indefinitely, and so, like, I want to make the claim that I think Facebook generates more capital than they need to run and make improvements to their social networking application as itself, and that if you could think of maybe some sort of like Facebook social networking app that was like more of a public utility, that could be better for the world. So I think we can sort of think about combining software tools like the ones we've been talking about and minimal sorts of legal tools for instantiating and modifying the firm with modern ideas for the firm, which is like, you know, things like democratic ownership, platform cooperatives, like a democracy. I think there's a lot of experimentation to do here. So the project that I'm working on with Glenn Braun is called Ours, and sort of firms founded on the labor theory of intellectual property. So the ideas are pretty simple. I set a price for my intellectual property at the time of creation, sort of like in the form of like a dollar amount inside of a pull request. And when my work, and I have a license associated with that work, which states that at time of full compensation, my work is released to the public domain. And then I may license my property to multiple organizations, and in return I might receive something like money, the promise to the share of future revenue, or some sort of rights within the organization. And I really want to build and highlight that rights because that really relates to everything that we've been talking about today, and sort of object capabilities and sort of things that we can do inside of these modular governance structures. So in Ours organization, then, you could think of as a collection of works licensed from individuals, packaged and priced according to the governance of the organization, with the stipulation that sort of once the prices have been paid, those works become free. And so the claim is that removing barriers from forming these types of programmable organizations will create competitive alternative to platform capitalistic monopolies, and we'd be able to create something like something similar to the sharing economy of the last few years, but as like a publicly owned utility and not as some sort of larger enterprise. And so that's kind of like what I'm really interested in. My heart is in this type of technology, and yeah. So yeah, that's all we have. Thanks so much for organizing.